Okay. So that completes the part on shafts. The next part, which I think I can complete today, is miscellaneous shaft components, set screws. You've probably seen a set screw. It basically used to connect to surface, usually a shaft, to something else, and they rely on compression to clamp to surfaces. So example is shaft and collar. You would have a set screw. Uh, the best way to show this is the following figure. Let's assume that there's a shaft. This. And then there's a collar. This is the side view. So there is a set screw which basically keys in, which sort of holds the collar in place with the shaft. So that's the set screw. Okay, so clearly it's going to transmit torques because the shaft is rotating. There is going to be a force because the set screw is now going to resist that. It's going to transmit the force from the shaft to the collar. So let's call this shaft. The red thing is the collar. And then let's say that the diameter of the shaft is capital D. So we can compute the relation between torque, torque, F is force. It's called holding force. Oh, holding force. And D is diameter. Yeah, it's not very, it's kind of obvious how that equation comes. So if you know how the set screw is used, if you know the torque which is going to be applied, you know the diameter of the shaft because you designed it, then you can actually use this table to select a set screw. So this table, next table, which I'm going to show, is basically gives you, well, it gives you the size number. So this is like a catalog, a torque, which is something which you know because you will power the shaft to have certain torque, and then you will also compute the power. The power here really means, look at the units. It's lbf, it's unit of force. Okay, so we have torque equals F T divided by 2. So essentially, torque will be known. The holding power you should know. And then the question is, you need to basically figure out the size, which comes from the table. That's pretty much what it is. If you find something which is in between, let's say your design gives you 225. Okay, 225 is not available. You only have 200 and 250. You want to choose the bigger one, not the smaller one, because then it will break, because it's the bigger diameter, the larger force it can take. So that's the set screw. Next we go to keys. Keys are used to transmit torques from shafts to other elements. So you can see how it works. So the shaft is shown here. This is the shaft. This is the other element. It's basically, the key is here. It basically sits inside the shaft, a part of it, and some part of it sits on the other component, could be a collar, and it basically is able to transmit the force because of the way it is designed. There are lots of, well, the different types of keys. Here's a square key, square because the cross section is a square, WW. This is a flat parallel key, parallel because all the lengths are parallel to each other. There's a tapered key. So what you see here is actually there's a taper here. It goes from here, it goes down. There's a gib head key. This one has like this protruding part which helps you to remove the key if at all you need to remove the key. Some shafts you can use a round key, and then there's a profile key. Another famous key is the Woodruff key. It is shaped like a semicircle. The advantage of this key is that it adjusts to any taper in the hub, okay, which is good because you then don't have to make it very high. You don't need high tolerancing on the shaft because it fits. The problem is that the depth of the key, you can see it's just, you need to cut so much inside the shaft. So the depth of the key weakens the shaft. Change in geometry, stress concentration, high stresses. That's what you don't want. But on the other hand, it is more, you don't require so much dimensional tolerancing for this key. Okay, so now we'll look at analysis of key and solve a problem. That's we're getting to. So this is how it sits. Let's assume that there is a shaft. So cutting here, and then the key is right here. Okay, so there is a groove here. That groove lets you put the key inside. So if you look at the side view from this side, then all you see would be a circle, and then the key would sit like this. Let's say that's the width of the key. Let's say this is the thickness of the key. Okay, it's subjected to a transmission force, which we'll call Ft. Ft, this is thickness. There's also a crushing force, Fc. So let me write those things down. Ft force due to transmission torques. It's a compressive force, as you can see, and it can be computed, and we're going to do this calculation from external torque. Let's call that torque T. External torque T. Fc, which I shown in the figure, is a force due to the key fitting inside the keyway. Okay, if there was no force, or it was not fitting snugly inside, then there would be no force, in which case it's not doing its job. It's going to lead to a play, and that play is not really good when you're trying to move things around. So this is also a compressive, it's actually a compressive crushing force. It is actually kind of difficult to determine. Okay, so it comes because the key is probably slightly bigger than the groove, and so when you try to put the key into the groove, it is held on by forces, and that force is just sort of hard to compute. Uh, it's hard because there are probably theories which do it, but at least in this course, which is very empirical, we're not really uh, using those advanced theories. Okay, so now let's look at the actual stresses, which will now help us to figure out first stresses and then the factor of safety for keys. So let's get started with that. Okay, so here is a shaft. with the key. And let's say that the diameter of the shaft is d, so the radius is d divided by 2. So here's the key. Okay. Thickness, width, length. Okay, and then if you remember the force which I showed here, this force was horizontal. So I'm going to put that force in here, Ft. Okay, it also acts like this, Ft. Okay, so so what this force does is we're going to compute the effect of, well, it leads to a shear. So when you apply that force, this cross section here, the bottom half is going to be subject to shear force. The shear force is basically, actually, if you see, it's going to be this way, tau, but then it will lead to a complementary shear, which will be acting in the opposite direction. Just try it with a different pen. So this force will lead to a shear torque, and then that shear will also lead to a complementary shear this way, right? Because shear always comes in a pair. Okay, so how do we compute that? It's actually a straightforward calculation. First of all, yeah, so first of all, the shear is what? It's the force divided by the area over which acts. So the yellow area. The yellow area is the length times width. Okay, but we also know from, so this is A, B. Okay, so this comes from B. But from A, we can also compute a relation between torque. So this is subjected to a torque. The torque is Ft times radius, so d divided by 2. So this comes from A. Yeah. Ft. So what we'll do is we have two equations. We'll eliminate Ft in the two equations shown by star. So if you do that, you have LW tau. So I just moved this on the other side equals 2t. So again, move this to t divided by d. Okay. Eventually, what you get is tau equals 2t divided by dWL. That's the formula which gives you the shear force or the shear stress as a function of the external torque. Okay, that's one kind of force. There's another one which appears. I'm going to just reuse these figures. Copy. Okay, now I'm not focusing on the shear stress, but we'll focus on the compressive stress. So the same setup, but now we're looking at the stresses which would effectively crush the key. So we'll assume that See, so we can see that I'm just going to assume that half the key is sitting inside the shaft. So it's let's take this. So it's this part which is sitting inside the shaft. So this part is going to crush. This part is going to crush because of Ft. So sigma C is, let's say, the compressive or crushing stress. So from okay, let's write the equation for that. Sigma C is Ft acting over the I guess the orange region shown there. It's only going to be half of this, just half of this, T divided by 2. So sigma C is the force Ft divided by the cross section over which it acts. It only acts over half of that region because half of that sits inside this groove. So it's going to be the length times T divided by 2. Okay, the better way to draw it is this way. Okay, so this is T divided by 2. It's this area. That's L. So L times T divided by 2 is the cross-section area. This is the orange area. Okay, so this comes clearly from B. And we also know from that the torque is Ft times T divided by 2. This comes from A as before. Okay, so we have two expressions. Let's call them tilde. Eliminate Ft from tilde. So essentially move that up. Sigma C L T divided by 2 equals 2T divided by D. So solve for sigma C. It's 4T divided by D times L times T. So this is a formula for the crushing strength. Okay, so let's give that, let's call this 1, call this 2. We can actually, so from 1 and 2, so 1 is giving you shear stress, 2 is giving you compressive stress. You can actually take the ratio and get 2W divided by T. Okay, so if W equals T, the width is T, then the compressive stress is actually twice the shear stress. Okay, we're almost there. Let's compute the factor of safety and then solve a problem. Okay, factor of safety, so design factor. So 1 for crushing. So here N is Sy divided by sigma C. So I'm just going to put the formula for sigma C. It's 4 divided by T dTL. So N is Sy dTL divided by 4T. That's the formula. Okay, that's one. The second formula is based on shear strength. So the factor of safety there is SSY divided by tau. So SSY, the tau we've computed in the past from function of torque, dWL. So N is SSY dWL divided by 2 times T. Okay, so we have factor of safety based on two criteria. Clearly, you need to use the factor of safety to make a determination on something like maybe the length or width or T, depending on what the problem is. And we'll come to that in just a bit. Now, there's SY here and SSY. We actually had a relationship between them from, if you look at the notes from distortion energy theory, distortion energy theory, we had computed a relation between SSY and SY. It's 0.577 SY. Okay, so we can use this. We don't need SSY. We can compute it from SY. Okay, so let's do one problem, and that would be it. It'll be end of this chapter on shafts. Okay. A shaft of diameter 1/16th of an inch, so that's 1.4375 inch, will have a 3/8 inch square key. Compute a suitable length. So the length is unknown. Assume that the yield strength of the material is 54 kpsi. Yield strength is 54 kpsi. Torque is given. It's 4,200 lbf inch, and the design factor is given as 1.5. So we need to compute the length, and we are given given a square key. So if you look at square keys, a square key is here. So you can see it has a width and a thickness. So thickness is the same as width. So what we can write here is the width equals thickness equals 3/8. And then I think the diameter is given. So D is given. It's 1.4375. And you can write the reason is the square key. Okay, so this is the unknown. Okay, so how do we do this? Well, there are two things we need to consider here: crushing strength and the shear stress. So if you go and look at the formula, there is a formula for how the crushing strength determines the factor of safety, and there's a formula for how shear strength determines the factor of safety. So let's do the computation for the length based on these two formulas and see what we get, and then we can choose one of those two based on simple reasoning. So let's do that. So let's do design based on crushing strength first. So we have N equals SY dTL divided by 4T. I just copied the formula which I derived earlier. We can solve for length. It is N or 4Tn divided by SY dt. The length is 4 times 4,200. N is 1.5. SY is 54 10 raised to 3. And D is 1.4375. And then the thickness is the same as width, 3/8. So length comes out to be 0.866 inch. Okay, that's one of the, that's an answer based on just the crushing strength. Now we could do the same design based on shear strength, which we'll do next. So this is let's call this 1.866. Let's do design based on shear strength. So that would be N equals SSY D times W times L divided by 2 times T, where SSY is 0.577 SY. So we can solve for L. It's 2TN divided by 0.577 SY times T times W. Okay, so what is that? It is 2 times 4,200, 1.5, 0.577. SY is 54 10 raised to 3. D is 1.4375. And the width is 3/8. So doing this calculation gives L equals 0.75 inch. This is 2. Okay, so what we found is design based on crushing strength L equals 0.866 inch. Design based on shear strength L is 0.75 inch. So which one would you choose? 0.86 or 0.75? Okay, so given two values, you always choose the larger value, because larger the value, the better it can carry the stress. Same for the diameters. If you have two diameters, you always choose the larger of the two. Choose larger of the two. So L equals 0.866 inch is the answer. In fact, if you actually if you choose the smaller one, 0.75, and you do the calculation uh, for the crushing strength factor of safety, you'll see you get less than 1.5, which violates what we set out for. So this is the answer. Okay. That's it. So this basically concludes shafts. This part, keys, is not part of your exam 3, but everything shafts is part of your exam. Next is going to be bearings.